In this video, we will cover the fundamentals of Python programming. We will explore key built-in data structures, such as lists and dictionaries, provide a brief introduction to object-oriented programming, or OOP, and delve into two essential libraries for machine learning, NumPy and Pandas. Let's get started by talking about lists in Python. A list in Python is an ordered collection of elements which can be of different data types. And the most important thing to remember is that you can add elements, remove or modify elements of a list. The way you can define a list is that first you choose a variable name. Here I want to call it a list. And then we use these square brackets. So once you see these square brackets, you know that you're defining a list. And here, obviously, we have 4 elements. And you can see that also we have even a character string, which is shown by these double quotes. And here we're going to do a couple of things. We're going to print this list and then go to the next line, look at the length of this list, which means that how many elements we have here. Obviously here we have 4, but sometimes we need to figure this out. And then look at elements that they are at locations 2 and -1. So let's run this cell. So the first thing is obvious, we just printed this list. Then we are looking at the length of this list, which means that the number of elements that we have, and that's 4 as expected. But what is the result of this part? So we are looking at the element at location 2, and we see that we get 5. And this is because in Python, indexing starts from 0. So this means that this first one is location 0, location 1, and then location 2. And therefore, we get this 5. The interesting thing about Python is that you can also use negative indexing. And you can see that when I say -1, I actually get the last element in this list. And so therefore, the way this works is that the negative indices, we have -1 as the last element, then -2, -3, and -4. So we are able to both index from the beginning of the list or from the end of the list. And this is very helpful because if you want to just, let's say, do something to the last element in a list, we can do this easily using this -1 index or location. The other data structure that we have to cover when we talk about Python is a tuple. A tuple is very much similar to a Python list, and the way that we define it is using these parentheses instead of square brackets. But the most important thing that you have to remember is that once you define a tuple, then you cannot modify them anymore. So that's really helpful if you want to create an order list of or set of elements in a way that you don't want to change them later on. So you can see that here we print this tuple. Even we can use type, and this is like a Python built-in function. So anytime you don't know the type of an object in Python, you can just type, and then that object that you have. So here it says that this is a tuple. And then if you look at element at location 1, that's actually the second element because its indexing starts from 0, and that's going to be A. And here you can see that if for some reason I want to change, let's this second element to be like B or something else, you immediately see that we get this error message, which says that tuple object does not support item assignment. And that's what we just explained about a tuple, where once you define a tuple, you cannot modify or change one element. The other data structure which we use a lot in Python programming is a dictionary. The key difference here is that a dictionary is an unordered list of key value pairs, meaning that in this case, we do not have any more ordering, so we cannot say what the second element is or the third element. And instead, the way that we can retrieve elements is using this idea of key value pairs. And you can see here, like in order to define a dictionary, you can use curly brackets. instead of a square brackets that we used before. And now we can use these key value pairs. So I add this key, which is fall. Let's say this is the number of enrollments in the course. And so in the fall semester, there are 50 students. And in the spring, so that's a new key, there are 80. And so here, let me just comment this line for a second. If I print this, you can see we have this curly bracket, which means that this is a dictionary. And now if I want to know the corresponding value for fall, I just need to use print dictionary key fall, and then you can see that we get the value, which is 50. So this is very much helpful in terms of being able to easily retrieve elements without remembering the ordering of elements. And as always, if you don't know what, for example, this object D is, you can use type D, and you can see that it's a dictionary. So that's something very helpful whenever you don't know the type of an object. Another idea that or topic that we have to talk about when we talk about Python programming is a for loop. So a for loop is very helpful when we want to iterate over a sequence. This can be a list, tuple, string, many different types of what we call them as iterables, means that things we can iterate over them. And obviously, the idea is that once we have a for loop, then we can, perform some operations for each element in the sequence. And since Python is a language that's very much similar to plain English, you can see that if we have, like, let's say this list, which contains 5 elements, and I just say for item in this list, and I want to just here print them because I want to make sure that it's something simple, this will do exactly what we expect. So it's going to retrieve each item or element in this list and print that item for us. Now, usually you want to do something more interesting once you recover this element, but for now we want to do something as simple as just printing them. So if you want to iterate over, let's say, a list or a tuple, what you can do is just say for whatever name you want. This is totally optional in that list. So that should match the name of the list that you want to iterate over, and then print the variable name that you selected here. However, there are other ways of implementing a for loop in Python as well. And one of them is using this len function and then applying that to the range. So the reason that we want to use this is that what we have covered here, we are going to retrieve each element, but sometimes we also want to know the index or location for that element as well. That might be something that is helpful or useful for us. In order to do that, you can use this len function to find the number of elements that you have in this list. And then you use the range function, which generates a sequence of numbers from 0. Remember, that's very again important. That always starts from 0 by default, up to, but not including to that len of that list. So this means that here, if we have, let's say, 5 elements in our list, this range will create a sequence of numbers starting from 0, 1, 2, 3, and 4. So this means that we actually have 5 indices here. But since we start from 0, then the endpoint should be the number of elements minus 1, so that in total we have number of elements. And here you can see this. If I run this cell, these are the indices for these 5 elements that we have, 0, 1, 2, 3, 4. And now if you want to retrieve the elements corresponding to these indices, you can pass this index to the list, and this is very much the same as what we did originally. But the nice thing here is that we have access to the index of each element as well. And this is something that is helpful in some scenarios. Another thing that we would like to cover here is the idea of conditional statements, which means that if, elif, and else. So this is a very simple idea in a sense that let's say you have a variable that is 5, and you want to write a piece of code that if this x is less than 0, if it's negative, then print negative. elif means that now you have another condition. If x equals 0, then we want to print 0. And remember, if you just use one equality sign, that's assignment. But if you use two, that means that this is a comparison operator. And else, meaning that if none of these two conditions are met, then you print positive. So you can see here, obviously we have 5, it's positive, but if I make this -5, we get negative. So this is something that we're going to use a lot in this course too, right? It's just an if statement where you have multiple conditions, and based on those conditions, we want to do different things. And something that is very important in Python, we do not have any and keyword. So this means that the only way that we know what is included inside this condition is this indentation that we use, which is typically 4 spaces. But you don't have to be worried about this because if I just come to the previous line and press enter, automatically I get the indentation that I want. And this is one of the most important things to remember, that everything that should be included inside this first if statement needs to be indented with the appropriate number of spaces. And then once we are done with this, we go back to the beginning of the line. And we do this again for this elif or else, etc. And this also happens again when we want to define a function in Python. So a function is very much like a reusable block of code that we can use to perform a specific task. Let's say you want to, square a number. In this case, you want to be able to easily do this for any given number. So we define a function. The first thing you use is to put this def or def keyword and then the name of the function. And inside parentheses, you use input arguments. So in this case, it's easy. We have one input argument and we want to square this. So that's just this num. And then we use the colons here. So this shows that now in the next line, we want to define what we want to do with this num. And here we are using these two stars or asterisks, which is like exponentiation. So this means that we want to raise this num to the power of 2. And the most important thing when you're using function, in my opinion, is to remember to use return, because otherwise this function is not going to return anything. So in this case, we're saying that we want to return this new num, which is this square of the input. And once we run this cell, obviously we are not doing anything yet because we just defined how this function should work. And in order to be able to see if this really works or not, now we give an input, which is 4, and we call this function, and then we print the result. And since we use return, we should be able to see that we are returning this. Something that we can do just to show this, if I comment this line and I print the result, you can see that we get none. And this is a special type in Python, which basically stands for nothing, means that we don't have anything here to return. And that's just because we forgot to use return. That's why always important to make sure when you define a function and you want to return something to specifically use this keyword return. And in this case, we should be able to see what the result is. Something that is a really good programming practice is to document what your code is supposed to do. And the way you can do this in Python is using these triple quotes. And this is what is known as documentation string or doc string. And here it just explains that we want to calculate a number raised to the power of 2. You can add some comments and then return the result. So this is obviously very simple. But something that, for example, you can do is when you want to, let's say, both find the square and also, raise the number to the power of 3 as well. So in this case, we have to calculate two different numbers and we return both of them. And the ordering here is really important, right? Meaning that when we run this, we get two numbers. The first one is the one raised to the power of 2. The second one is the one raised to the power of 3. And obviously here in the doc string, we document this. And if I run this case, you can see that we get the result that we expect, 3 raised to the power of 2, 3 raised to the power of 3, which is 9 and 27. And the nice thing is that actually when you use a function and we return multiple values, the type of that object is a tuple. So that's another reason why you need to know about tuples, because when you return more than one output, actually by default, that's in the form of a tuple. So now let's talk about object-oriented programming or OOP. So in many cases, when we do programming, we use something called procedural oriented programming or POP, which means that we write line by line what we want to do. For example, we collect some data, we do some statistical analysis and so on. And so everything is just, line by line what we want to do. The problem is that if we want to make some changes, we have to be very careful, or we want to add some functionality or remove, then we have to, comment part of the code and add some part of the code. So it gets really messy to use in real world, especially if you really care about versatility and reusability. And therefore, one of the important things when you talk about machine learning, data science, AI, is this idea of object-oriented programming, which means that we want to code as a collection and interaction of objects. And this is something I already use. I called multiple times objects. For example, let's check the type of an object, because obviously Python is an object-oriented programming language. So what is so special about objects? The most important thing about objects is that they incorporate data and what we can do with that data into these objects. Therefore, we have two key concepts in object-oriented programming. One is a state, and the other one is behavior. So a state means how the object looks like or what properties it has, and behavior means what we can do to operate on that. And in Python and machine learning in general, because libraries that we talk about are based on Python, we call states as attributes, and these things are variables, and we call behaviors as methods, and these are functions. So here we have a summary of the whole picture. So classes are blueprints or templates for creating objects, right? So how we can create objects, but we don't necessarily creating objects right away. That's just, template or blueprint. And objects are instances of a class, right? So once we have a class, we can instantiate it, and that's going to give us an object, and we can create many, many objects. And then each object has attributes, and those attributes are variables that contain or store some data or information or properties. And methods are functions that defined, within that class, which means that now we can perform some operations. So that's kind of like the big picture about object-oriented programming. So first we have to define a class, or somebody has defined it already for us. We are going to create objects, and each object has some attributes, and then also we can perform some operations on these objects using these defined method that are part of classes. So let's look at this idea using a simple linear regression problem. And this is something that we already mentioned, right? That the simplest case, if I go back to one of the examples that we have, is that, well, we have on the x-axis an input feature or predictor. On the y-axis, we have an output. And let's say for simplicity, we want to extract the relationship between input and output using a linear equation or a line, which has a slope and intercept. So with that in mind, so this means that now the assumption that we make for our model is that the output of our machine learning model should be some intercept, or there's a y-intercept, plus a slope times the input. And before we use the general variable named theta, and I intentionally here use beta to show you that the names of these variables really do not matter, right? So what we're really saying is that we have a model parameterized by intercept and a slope. And also we have a training data set which contains input, output, occurs. In this case, because the problem is really simple, you can see that we can find the optimal values for the intercept and slope using these two equations. So the numerator of beta 1 has this form of multiplication of individual elements of this training data set subtracted by the sample mean. So x bar is the mean of all the xn's, y bar is the mean of all theyn's, and also normalized by the sum of the square of differences between each xn and its mean. So this looks very much like a variance term if we use the right scaling, and the numerator is more like a correlation term. And then once you find this optimal value of beta 1, you can plug it into this equation to find the optimal value of beta 0. So we're going to have a problem in our homework assignment to actually prove this. And this is also, you can verify this through this textbook. But for now, we want to implement these using the concept of OOP. All right, so obviously we can write this as a procedural oriented programming line by line, but I want to use more an advanced technique using object-oriented programming. So in order to define our class or our template or our blueprint, we use the keyword class. And then we choose a name. Here I call it simple linear regression. That's the name of my class. And the very first thing you want to use is this special function, which is def because it's a function. We want to define a function. But then it has this underscore underscore init underscore underscore. And also you have to provide this self here. So what we're saying here is that this model has this beta 0 and beta 1. And at the beginning, we don't know what these two should be. So I just call them none. So as mentioned earlier, none is a special kind of like a type in Python, which stands for nothing, basically lack of value for something. And the reason that here we use this underscore underscore is that this is a function that has a special meaning in Python. And that's why it has this structure of starting with underscore underscore so that you do not define your own function and that coincides with this name. And then what is this self here? So this doesn't necessarily have to be called self, but it's a very common programming practice to call it self. And the reason being that, well, when you define a class, you want to provide a template for future objects. So at this point, you don't know exactly what that object is. So you need to call it something. And therefore here, it's very common to call this self. And this refers to the future objects of this class. And what we're saying here using this dot notation is that this self has two attributes. As I said, these are variables, one called beta 0 and one called beta 1. So, and right now we don't know what they are because we just started the problem. However, we can actually train our model. So that's our method or function. You obviously have to pass self because that's something that should be accessible through your code. And then you provide your inputs, which we show them using X, and outputs, which we show them using Y. So X is a list or array of input features, and Y is a list or array of target values or outputs. And since in this case, we have a simple linear regression problem, X and Y are just two one-dimensional arrays. Later on, we're going to cover cases where this X for each input can have multiple features, but in this case, right now, we only have one feature for each instance. So in order to do this, now here, the rest is kind of like a straightforward. So first you look at the number of elements you have in X, which is the same as the number of elements in Y because there is a one-to-one correspondence. You find the sum of values in X divided by the total number of samples. That's your sample mean for X, sample mean for Y. Now we have to find the numerator and denominator for beta 1 according to the equation that we have. And one of the easiest way you can do this when you want to pick one element from one list and then corresponding element from the other list is using the Python zip function. So what this does is that it gets or accepts two lists, one X, one Y, And then it returns an iterable, meaning that now you can use a for loop to go through them, where each element of that iterable has one element from X, one element from Y. So that's why here you can see that we are saying for X, Y, Y, I in zip of X and Y. So this is literally saying that we have these two lists and combine the corresponding elements and pick those corresponding xy values and then compute the sum of xi minus x mean, yi minus y mean. And that's exactly what we have here. So that zip is allowing us to perform this summation by picking up corresponding elements xn and yn. For the denominator, we can do the same thing, except that now we're only looking at elements from the list X. So we don't have to use zip anymore, but it's the same idea. We iterate over the elements of X using this for loop and find the denominator. And that's the really cool thing about Python because, the previous version that we saw, we had for some item in some list column, we want to do something, but you can actually write the whole thing in one line. So that's a very nice thing about Python, make it much more readable. And then now we're going to actually find the value of beta 1. And remember, it's self.beta 1 because that's the attribute, which is this numerator over denominator. And once you have this, you can find self.beta 0. So this means that once you create this object and call the fit method and provide your two lists of x and y values, now you know what these beta 0 and beta 1s are. And now we can pass this information to the predict method. And this method obviously again needs self because it needs to know what beta 0 and beta 1s are. And now we have this new instance X, right? So we want to predict the output for a new instance. And since it's a linear model, now we can see that for each element in this list X, if we have multiple, now we want to find this beta 0 plus beta 1 X. So this is very much the mathematical equation that we just had in the form of object-oriented programming. So let's look at an example usage. So let's say we have these two arrays, X and Y. So X contains inputs and Y contains outputs. It's obvious here that the way that the relationship between these two is that if we multiply 1 by 3 and then add 2, we get 5. And the same thing with the rest of these elements. But we want to see if our code also can do this for us. So we're going to create an instance of this simple linear regression that we just defined. So in this case, means that this is our class and this is our object. Now we're going to call the fit method to pass in x and y to be able to find beta 0 and beta 1. And now let's see what the output is for a new input, which is 10. So we're going to print all these things here. So you can see that our beta 0 is this model.beta 0, which is 2. Our beta 1 or slope is 3, which is exactly what we have here. And also the output for this new input is obviously 3 times 10 plus 2, which is 32. So far we have used Python list, especially when we had an array of inputs and outputs. And although this is feasible for simple cases, but we have a big problem in the sense that in many cases we have multi-dimensional arrays of data. For example, if you look at like a color image, we have, this is what is known as RGB. So this means that we have 3 channels, and each channel we have image height and image width, which means that in total we have a 3-dimensional structure. And because of this, if you want to use Python lists, you can, but it is very inefficient because Python lists are really useful when you have a 1D collection or one-dimensional collection of items. And they are not really designed to perform mathematical operations or linear algebra operations. And therefore, there is really need to have a Python library where we can work with any dimensional array with a lot of mathematical functionality. And that's why throughout this course and during machine learning, we always need to use NumPy. So the two common forms here of NumPy's arrays, one is a 1D array, which is this case where we have a vector in a mathematical case, which means that we have A1, A2, AN. So this is a column vector right now with n rows and one column. Or we can have a matrix, which is a 2D array, and we have to use two indices here, one for the row location and the other one for the column location. And this is what is known as Rn by m, which means that we have n rows and m columns. So let's see how we can do this. So the first thing you want to do when you want to use something like NumPy is to first import it. And you're more than welcome to import NumPy without any additional things, but it is common to use an alias in some cases because you can then save a lot of space. And it's common to import NumPy as NP. So this means that we import NumPy, and from now on, we want to use this alias name, which is NP. So inside NP, we have this thing called np.array, which is what you can use to create NumPy arrays. And you can pass in a Python list in the first case, where now you have this A. And in the second case, we are actually, again, giving a Python list, but now the first element of list is another list, and the second element is also another list. So if I look at the shape, so this dot shape is an attribute, which means that tells us the shape of this array. You can see that the first one is actually 4 comma nothing, which means that it's a 1D array with 4 elements. The second one, this uppercase A, is 2 by 2 because it's a 2D array. And if you look at type, it tells you this is NumPy ND array. So that's exactly this NumPy n-dimensional array that we talk about. So if you look at what they are, so you can see that this lowercase a is just a vector which has 4 elements in it. And then if I print the uppercase A, you can see that now we have a 2-dimensional array. And I know that this is a 2-dimensional array because I have 2 square brackets here. Whereas in the other case, I only have 1. So that's one of the things you can really use to immediately identify how many dimensions you have in your NumPy array. If you only have 1, it means that this is 1D array. If you have 2, this is 2D, and you can also extend this to higher dimensional cases. And something I would like to very much emphasize here is that in the case that we have a 1D array, NumPy does not like to think about this as a column vector or row vector. This means that we have a 1D array, so there's no notion of columns and vectors because it's not 2D. However, in for example, linear algebra, right? If we have, let's say, what we have here, for the 1D array, we can also think of this as a 2D array with only one column. So this is actually a matrix 2 that has only one column. But Python and NumPy, they do not think about this in this form. So if it's 1D, it's just 1D, meaning that there's no notion of rows or columns. And if it's 2D, now you have rows and columns. Okay, and there are also other ways to find the number of dimensions or axes in your NumPy array. And one of them is using this ndim attribute, right? So this means number of dimensions. And if I run this, you can see that the first one, the lowercase a, has only 1, and the uppercase a has 2. Something that we want to do in some cases is to reshape our NumPy array. To see what this means, so let's look at actually one of the cases that's easier. So let's look at the lowercase a. So this is actually a 1D array which has 4 elements. But let's say for some reason we want to make this 2 by 2. So then you can use a dot reshape and then provide the new shape that you want to have. So if I run this, you can see that now this is 2 by 2, right? So this means that now we have our first row, and then these two go to the second row to make sure that this is 2 by 2. And if this is not possible to do, So you will obviously see an error message that says that cannot reshape an array of size 4 into shape 2 by 3. So Python is actually very smart in terms of understanding, that there is a big problem here, and we cannot reshape this array. And that's the same thing also with the uppercase A that we have. So if you look at that, what it is in it right now is a 2 by 2. And let's say you want to make these one-dimensional array. So we can just say that I want to reshape these to 4, comma nothing, which means that now this is a 1D array. There's also a lot more functionality here. For example, if you want to see if two arrays are equal or not, here we can use np.arrayEqual. If you look at it, A and B are very much the same. They're 1D arrays with 4 elements. Therefore, we get true. You can also use a lot of mathematical operations and linear algebra operations. One of them is transpose. So if you look at it, this is the original matrix A. And then the second one is the transpose, where we switch rows and columns. For transpose, you can also use the .t here. That will also do the same thing. I personally like this one more because it exactly says that we want to transpose A, but if you use a.t, that's the same thing too. You can also, from NumPy, inside NumPy, there's this module called linalg for linear algebra. And this has implementations of many linear algebra algorithms and routines. For example, one thing is to find the norm or length of a vector. And since here our x has two elements, 3 and 4, the norm is the square root of 9 plus 16, which is the square root of 25, which should give us 5. Yeah, so as you can see, this calculates what is known as the L2 norm in linear algebra. And the list continues. For example, you can also find dot product or inner product between two vectors. If x and y are numpy arrays, obviously that's the definition of the dot product. We already defined x here. And if I define y and say np dot dot, now you can see that we have the dot product. And we know that, for example, for the vector x, um, if I find the dot product of a vector by itself, that's the Euclidean norm of square. So that's where we get 25. So if you want, for example, implement the norm by yourself, you can just find the square root of this dot product of x by itself. The other thing is, for example, matrix multiplication. That's something we're going to use a lot in this course. So if you have a matrix, multiply this by a vector. There are two ways to do this matrix multiplication. One is that you pick the first element of this row vector, you multiply this by the first column of this matrix, and do the same thing with the other elements and add all together. Or you can think about this matrix vector multiplication as the dot product of the first column, or say first row, the dot product of the first row of this matrix and this column vector that you have, right? So that's where you get this index from I from 1 to n of A1. So the 1 means that this is elements in the first row, and you multiply this by the corresponding value of xi. And obviously for the last element, you pick things from the last row, which is index m, and you do this element-wise multiplication. And we're going to use both forms in this course. So we sometimes use the first form, where we look at the columns of this matrix, and sometimes it's easier to look at the rows of this matrix and then the dot product between this vector that we have here. And in terms of matrix multiplication, you can use this matmul, which stands for matrix multiplication here. We are going to multiply a and x, and you can confirm that both ways should give you the same exact result. The other thing that we're going to use is pandas, and we have a full lecture on this, but here just to give you the basic ideas. So pandas is very much used to store data sets that are in tabular formats, right? So if you have, like, let's say a data set where you have number of years of education, number of years of experience, and many other information for employees and you want to predict their salaries, it's very much easy to think of this as a Excel file where you have columns with their names, and now each row is one instance or one employee in your company. And although data frames, which is what we really need from pandas, um, can be thought as a two-dimensional data structures with different columns and rows correspond to different instances that we have. So in order to create a data frame, there are multiple ways, but one of the ways is to start with a CSV file, which stands for comma separated values. So here you need to make sure that you have this credit.csv in your directory. And if you use this read CSV method, it will read that CSV file. And now we can use df.head to look at the first 5 rows of this data frame. So here you can see that we have these column names. So this is a problem where we want to be able to predict the balance on credit cards for different people based on several features or predictors like income, limit, rating, the number of cards, age, education, marital status, region, etc. Right? So you can see that we can, for example, just use a NumPy array to save these, but then we have to memorize that the first column corresponds to income, the second corresponds to limit, and that's not a really good way of storing and sharing your data. So that's why Pandas data frame is perfect. It's very much like an Excel file, and you can actually open a CSV file using Excel if you just want to know what it is before working in Python. And also, if you want to know how many rows here you have, how many samples or observations, you can see we have like 400 of them. If you want to just pick the one of the columns, you can just simply use this square brackets and use the column name. You can see that here we have the 400 elements corresponding to these income values. If you want, for example, create a histogram plot to get an idea of the empirical distribution, you can use .hist, which just stands for histogram. You provide the number of bins. So you can see that here we have, this information about the incomes here we have. This is in thousands of dollars. So it starts from some total like, around 25K or less 20K to 175K. And as you expect, it's obviously this data set is skewed, right? So, it's obviously more values towards the smaller values that we have in our range. And then also it's very easy to work with a subset of observations or rows in a data frame. So here you can see that we use this conditional statement that we are saying that, well, we want to pick the rows of this data frame where the income value is less than 100, right? So we want to only study people that they make less than $100,000. So that's our condition. And this will give us a bunch of trues and falses, depending on whether this condition is true or not. And if you pass this to our data frame, you can see that now the ones that we have should be all the cases where the income is less than 100. And obviously you can see that we only have 363 of them. So out of 400 rows or samples in our data set, we had to get rid of 37 cases. The other thing we also can do, this is when we use plotting. So for plotting, we use matplotlib, and the way we use this is we import pyplot as PLT. This is very standard we use. Is that let's say, we want to, form a machine learning problem where our inputs are the limit that we have and the outputs are balanced. So we want to see if we can just use the credit limit information to be able to predict the balance that people carry on their credit cards. So one thing that we can use is a scatter plot, which means that we're going to get each element of this X list and each element of the Y list, and we're going to plot them in a two-dimensional space. And this should give us an idea of whether there is any kind of relationship between these two. So obviously, as you can see, that people that they have higher limits, they do overall tend to have higher balances on their credit cards. Obviously, there are some cases that, they do not really conform to this, but overall, you can see that we have this positive trend. And the nice thing is that since you define your own, class for simple linear regression, you can instantiate that again, as we do here. Use .fit to find beta 0 and beta 1 that we just discussed. So you can see these values, and you can see the slope here is positive. So yeah, there is definitely a positive relationship. And then you use the scatter plot to plot those data points. And now, since you want to draw a line, you only need 2 points on that line. So let's use one of the, kind of like the small values and large values on the x-axis, and we pass this to beta 0 plus beta 1 times x. And this should give us the plot of this line that we found for our simple linear regression. So you can see that here, of course, we have some, I would say abnormalities where, the balance is 0 for some of the people here. But overall, you can see that as we increase the limit, the balance increases. And this line seems to be a really good fit for this data set.